Hello, welcome to the fourth lecture on this course on Introduction to Quantum Physics. In the last two lectures, I discussed the experimental results. In the second lecture, I discussed the experiments black body radiation and photoelectric effect, which required that energy should be quantized. And in the last lecture, I discussed Bohr atom and specific heat of gases, which required that the angular momentum should be quantized. So, we are led to this requirement that energy and angular momentum should be quantized. Well, and also we are led to this picture that we cannot think of light as a wave. Of course, classically we have been thinking of light as a wave, but photoelectric effect in particular seems to tell that light also should sometimes be thought of as a particle, that we should think of light as a bundle of energy which comes and hits an electron, gets absorbed by the electron, you can say a completely inelastic collision, and then the electron comes out of the metal. There are other developments which took place soon after, but to understand some of them, we need to know one concept from relativity, the concept of energy in relativity. So, let us look at that first. In classical physics, when you have a particle of mass m and it is moving with speed v, we say it has kinetic energy half mv square. But in relativity, we have to think of energy in a slightly different way. We say that first let us consider a particle of mass m and it is at rest. Then in relativity, we say that the particle has a rest mass energy mc square. What if it is moving? Well, instead of velocity, we mostly talk in terms of momentum in relativity. Let us say it is moving with momentum p. Then the energy of this particle is square root of p square c square plus m square c power 4. And you consider the case when p, the momentum is much less than mc. Momentum, of course, we can write as mv. So, mv much less than mc, that is v much less than c. The particle is moving with non-relativistic speed. Then you can see that the expression for energy becomes mc square plus p square by 2m, and p square by 2m is nothing but half mv square, the kinetic energy that we have talked about before. So, in the non-relativistic limit, the relativistic formula for energy, it gives us the correct expression in the non-relativistic limit. How is momentum related to velocity in relativity? Well, it is not quite related as mv. The momentum is gamma times mv, where gamma is the relativistic factor, which is defined as 1 over square root of 1 minus v square by c square. And for a massive particle, v is always less than c. So, 1 minus v square by c square is always positive and gamma is always greater than 1, and it is 1 for non-relativistic particles. And when you substitute this expression for p in the expression for energy, you will easily, it's quite straightforward to derive that V by C is equal to Pc by E. So, the ratio of momentum to energy is equal to the velocity of the particle divided by speed of light. And now let us consider the case where we apply this to photons. Einstein, in explaining photoelectric effect, is asking us to think of photons as some kind of particles. So, let us apply this to photons, and photons of necessity, they are particles of light, so they travel with speed of light. So, V is equal to C for them, which means that for photons Pc is equal to E, and if you substitute that in the energy expression, you find that for photons we must have m equal to 0. So, we should think of photon as a massless particle, and for massless particles the energy is given by Pc, and now let us bring in Planck's formula where the energy is given by h nu. So, we have the relation Pc is equal to h nu, or we can write P, the momentum of the photon, is h nu by C, and remember C by nu is lambda, the wavelength. So, h nu by C can be written as h by lambda. So, for a photon, that is for a light quantum with the wavelength lambda, it has a momentum given by a momentum P given by h by lambda. So, this is what we get by combining Planck's hypothesis with relativity, that light of wavelength lambda has a momentum P, or we can also invert this and say that the wavelength and the momentum are related by lambda is equal to h by P. Now, let me take a little bit of go on a bit of digression and describe how we think of waves, how we mathematically describe waves. For example, we have the formula, let us say a wave is something, if I sit here and look at the wave passing by, I find that my position is fixed and wave passing by, time is changing. So, there is something changing here, but if I take a photograph over a wide range, I see an oscillating behavior as a function of space also. So, in the case of a wave, we see a changing behavior both as a function of coordinate x and as a function of time t. So, we always write wave in terms of both spatial coordinate and the time coordinate. We can consider two types of waves. One is a travelling wave, which we write as some amplitude times a sine or cosine function, and the argument of this sine or cosine function we write as k dot r minus omega t, and this is a wave travelling in the direction k. We can also think of standing waves, which I have written as b x of t. This can be thought of as some amplitude times a sine or cosine function in x, and here I have written sin kx and multiplied by sin kt. In the case of standing wave, there is a wave pattern, but it is changing with time, but the wave is not moving anywhere, whereas in the case of travelling wave, the wave is starting here and is moving somewhere else. It is like the waves in the sea which are moving, that is a travelling wave, and standing waves of course you get when you tie up both ends. But important point is that in the case of a wave, there is some physical object which is changing and changing sinusoidally both in the spatial coordinate as well as in the time coordinate. That is what characterizes a wave. And if you are thinking of waves in a stretched string, you have literally a small element of the string which is oscillating, and if you are thinking of a ringing bell, it is a small area of the bell which is oscillating like this. And you can think of water wave. I just mentioned waves in the sea. There it will be a droplet of water which is moving in an oscillating motion. And of course, you are all familiar with sound waves, where it is a molecule, air molecule, which is moving back and forth in an oscillatory behavior. I mentioned before that Maxwell showed that light is an electromagnetic wave. So, in an electromagnetic wave or in light, what exactly is it that is oscillating as opposed to the examples that I just gave? Well, Maxwell also provided the answer. He said that there is an oscillating electric field and an oscillating magnetic field, and both of which are changing together in an oscillatory manner, varying both along in the spatial direction as well as in the time. So, that is what he meant by an electromagnetic wave. There is an oscillating, there is a wave made up of both electric field and magnetic field, and in fact it also is required that the electric field and the magnetic field should be both perpendicular to the direction of propagation of the wave. That is what makes an electromagnetic wave according to Maxwell. Now, in all the waves that I discussed so far, there is a medium on which the wave is moving. In the case of water waves, the wave is moving in the surface of the water. In the case of sound, the sound wave is moving within this volume of the air. So, what is the medium in which this electromagnetic wave is moving? That was a question that immediately came when Maxwell proposed light as an electromagnetic wave. And to some extent, this question confused the people in the 19th century a lot. They made some very complicated theories which go under the name ether theories. But Einstein came and declared that these electromagnetic waves do not need a medium to travel. They can travel in space, in vacuum. So, there is sunlight coming from sun to earth, traveling a distance of something like nearly 200 million kilometers, but there is no medium between Earth and Sun, it is mostly vacuum, and light has no problem coming from Sun to Earth. So, the Einstein just declared that electromagnetic radiation, electromagnetic waves do not need a medium. I can have an oscillating electric field and a concurrent oscillating magnetic field in vacuum, and therefore, there is no need for any ether. So, that got rid of lot of the problems which occurred in the theoretical formulation in the 19th century. So, we have, that is why we use the symbol c as speed of light in vacuum nowadays, because that sets the standard for being the highest possible speed. Now, let us look at this question, electromagnetic wave or light. Is it a wave or a particle? How do we try to decide? Because Maxwell said light should be electromagnetic wave, whereas Einstein said light should behave like a particle. So, which is the correct description? This is a puzzling question, because there are series of experiments based on which Maxwell said light should be an electromagnetic wave, but then the photoelectric effect came, and based on which Einstein said we should think of light as a particle. So, and also let us consider the language that we are using. When we talk about light as an electromagnetic wave, we talk about its frequency or its wavelength, which are properties that we typically associate with a wave. But when we are talking about light as a photon, that is a bundle of energy in the particle type picture, we are talking about the energy of the photon and the momentum of photon, and typically this concept of energy and momentum we tend to associate with particles. So, we are using both these words, both sets of words, wavelength and frequency, while describing, you can say, the wave properties of light, and energy and momentum while describing the particle properties of the light bundle or the photon. So, it looks as if we are being opportunistic when it is convenient, when we are trying to describe an experiment which shows wave properties of light, we use the frequency and wavelength, but when we describe an experiment which describes particle properties of light, we use energy and momentum. So, can we have a picture which can involve both aspects? That is, that's what we would like to have. By the way, there's a famous poet called Alexander Pope, who was a junior contemporary of Newton, and he held Newton in great regard. So, he wrote a 2-line poem about Newton, sort of playing with some concept from Bible. Said, nature and her laws were hidden from sight, and God said, let Newton be, and all was light. So, praising Newton very highly. But then somebody from 20th century who got totally fed up with relativity, he added 2 more lines to this, said, but Satan was not long to fret and frown, soon Einstein came to put things upside down. Well, okay, the person who wrote this poem found it difficult to understand relativity, and it's not a easy concept, but if you think about it long and hard, actually special relativity is not that hard to understand. It requires a lot of effort, but you can make sense out of special relativity. But the idea that I just mentioned, how do we develop a description of light where sometimes it behaves like a wave and sometimes it behaves like a particle? How do you develop a common description which can do both jobs? That, at least to my mind, seems like something very, very hard to do. And in this case, there is a gentleman called de-Broglie who actually made the whole picture much more complicated. The discovery of electron I mentioned in the last lecture, it showed that electron is a point-like particle, it has no size and it has non-zero mass. So, it is like the ideal point particle that we try to deal with in Newtonian mechanics, a particle with mass m. And of course, we can associate momentum, energy and various other dynamical quantities to it. But what de-Broglie said is the following: if photons can have both wave and particle like properties, why can't a particle like electron, it should also have wave like properties? So, on the face of it, it makes some sense. Photons, which we classically think in terms of as waves, must have particle like properties. So, electrons, classically we think of them as particles, but they should have wave like properties. What is the basis for de-Broglie to say so? I mean, frankly, I don't know, but he made this proposal and he was convincing enough that people took this idea seriously and started applying it to in various contexts. Now, let us briefly consider how we think of particles. Particles, especially a point particle, is literally a point. So, at any given time, it occupies a single position in space. And if you take a object like this, which obviously is not a point particle, but in classical mechanics, what we try to do is we consider this object as a collection of mass points and held together by some invisible forces. And at the end of 19th century and early 20th century, when atoms were discovered, it was felt that this picture actually is correct. There are essentially point-like objects which are held together in solid bodies. And de-Broglie said, if we have such a point mass, he declared that it should have, and if it has some momentum p, we should associate a wavelength which we now call de-Broglie wavelength, which is given by h by p. So, Same formula which I mentioned earlier in the lecture for photon, that there of course we wrote it ulta. Photon has frequency nu, that means it has wavelength lambda given by c by nu, and the wavelength is related to the photon momentum. The momentum of the photon is given by h by lambda, and de Broglie sort of wrote it in the reverse way and said, if you have a particle of momentum p, then it should have, we should associate a wavelength lambda given by h by p. So, I mean, fine, you can tell me that I should associate such a wavelength, but what use is it? What can I do with such a wavelength? We will come to that in a minute, but what de Broglie tried to argue is we should not make a distinction between massive particles and massless objects like photon, which is, and number of photons make up the radiation. We should treat both of them on the same footing. So, the relation P is equal to h by lambda should hold for both photons as well as for massive particles. So, we know from Planck's hypothesis and relativity that P is equal to h by lambda for photons. We must also have similar relation for massive particles. So, for a massive particle of momentum p, we must associate a wavelength lambda. As I said, this is now called de Broglie wavelength. Lambda de Broglie is h Planck's constant divided by p. Now, so what if we give this wavelength to a electron, what will happen? Before that, let us briefly discuss what will happen. I have this object like this, why don't I see it as a wave? Why isn't there? Why don't I see its wave properties? Well, I can calculate the de Broglie wavelength associated with it. Instead of this, let us consider, for example, a cricket ball, or okay, let me take this only. This probably weighs about 100 grams, and I move it with some speed, let us say 10 meters per second, and I have the corresponding momentum, and the de Broglie wavelength is h divided by the momentum, and h, if you remember, is a very small quantity. It is something like 10 to the minus 34 joule second. So, when I take h by p, the corresponding de Broglie wavelength I get is very, very small. It is like 10 power minus 34 meters. And the smallest length we have been able to probe so far is 10 power minus 18 meters. So, if this has a de Broglie wavelength of 10 power minus 34 meters, there is no way I can measure that. So, we do not have to worry about de Broglie wavelength of massive objects. However, consider an electron. Electron has a mass of 10 power minus 31 kg, and if it is moving with quite a bit of speed, maybe 100 meters a second or so, or even larger, let us consider even larger speed, let us say 10 power 6 meters per second, which is still a non-relativistic speed, because speed of light is 3 times 10 power 8 meters per second. And the reason I mentioned 10 power 6 meters per second is that is typically the speed of the electron going around the nucleus in a hydrogen atom, or we can take a speed like 10 power 4 meters per second, which is roughly the speed of an electron moving around in a metal. So, what about the de Broglie wavelength of such electrons? And you find that because for these microscopic particles, since the mass is so small, the de Broglie wavelength is moderately large. It will be order of nanometers or angstroms, and it is possible to see the effect of de Broglie wavelength of such microscopic particles. One other interesting connection de Broglie made with Bohr atom is the following. Bohr, in making the proposal for his atom, he said that the stable orbits are those with for which the angular momentum is an integer times h cross. So, why should they be the stable orbits and why not other possible orbits with other angular momenta? Well, using the concept of de Broglie wavelength, you can provide a justification for it. You find if I, for example, I take a string, tie up one end and the free end I move up and down, and of course the frequency of moving up and down is in my hand, and you find that if the frequency with which I move up and down, then there is a wave which travels from my hand to the other end, and from the tied up end it gets reflected and comes back. So, the wave going this way and the wave coming back this way, if they are in phase, they will add and they will form a standing wave pattern, but if they are not in phase, then the two tend to cancel and there is no standing wave pattern. And you have studied this phenomena before, and you know that the standing wave pattern occurs only when the wavelength is related to the length of the string through an integer. So, de Broglie explained the Bohr orbits using this concept. He said that the stable orbits are those for which the circumference of the orbit 2 pi Rn is equal to a integer times the de Broglie wavelength, and in such case you have a standing wave like a circular standing wave like pattern, whereas in other cases you will not have a standing wave like pattern. This is illustrated in the figure for n equal to 3. So, this is a hand waving justification for believing in the de Broglie wavelength, that you take the Bohr radius and you take the radius of the Bohr orbits, from which, using the formalism of the previous lecture, you calculate the momentum and calculate the de Broglie wavelength, and you can show that the 2 pi times Rn is equal to an integer times the de Broglie wavelength, and that is the same condition as the Bohr quantization condition, which says that the angular momentum is equal to n times h cross. So, this is a partial justification for the concept of de Broglie wavelength. But well, that is not good enough, we need more solid proof. Where would it come from? By the way, to talk a little bit of history, both Newton and his contemporary Christian Huygens, they have made extensive studies of light, and Huygens favored wave theory of light, whereas Newton believed that light is actually what he called corpuscular theory, that is, light actually behaves like series of tiny particles. Both theories could explain the law of reflection and refraction, but because of Newton's other work, he was more prestigious. So, for about 100 years or so, people believed in the Newton's corpuscular theory, but in 1800, Thomas Young performed the famous double slit experiment, where he showed that when light from the same source passes through two slits, you get series of dark and bright fringes, and double slit experimental results, that bright and dark fringes, they could be explained based only on wave theory, they could not be explained based on particle theory, by assuming that light consists of particles. And soon after, there was the phenomenon of diffraction was studied, and diffraction also people could explain based only on wave theory. It could not be explained assuming that light consists of a particle. So, after interference and diffraction, people stopped believing that light consisted of particles until photoelectric effect came along some 100 years later. So, if you are asked to provide a litmus test of what is some object, some new thing that you have seen, and you are asked the question, is it wave or particle? Then to show that it is wave, you have to show that that new thing, it has diffraction and it also shows interference. For example, in 1895, Röntgen discovered X-rays. They were just some new form of radiation. But what are X-rays made of? And sometime later, people studying radioactivity, they discovered what were then called alpha rays and beta rays. But testing alpha rays and beta rays, they found that alpha rays are actually the nucleus of helium. It has a mass, charge. Similarly, beta rays were actually electrons. They also have mass and charge. But X-rays, there is no mass, and people soon realized that there may be a very high energy form of electromagnetic radiation. But then, if they are electromagnetic radiation, they must show diffraction. Do they show diffraction? That was the problem taken up by physicists, and a father-son combination in England called William Henry Bragg and William Lawrence Bragg, and also in Germany by von Laue. They studied the possibility of diffraction of X-rays. The question is, how do you make X-rays diffract? And here actually the formulae that I mentioned before, they come into use. So, people were able to calculate based on how the X-rays are produced, they were able to calculate the energy of the X-rays, and using Planck's formula they deduced the frequency of the X-rays, and from which they also deduced the wavelength of the X-rays, and found that X-rays have very short wavelengths of the order of angstroms, that is a factor of almost 1000 smaller than visible light. So, in order to observe the phenomenon of interference and diffraction, we need slits which are roughly comparable in size to the wavelength that we are looking at. I mean, in studying of optics, first thing we study is geometric optics, and in geometric optics we do not really worry about the wave nature of light. That is because the size of the objects we study in geometric optics, they are much larger than the wavelength of light. Therefore, the phenomena which occur, which are at the size of wavelength of light, we do not see them in geometric optics. But when the size of object with which the light is interacting, that becomes comparable to the wavelength of the light, then we begin to see this phenomenon of diffraction and then also interference. And once these phenomena were studied, what was called diffraction grating was built, which meant large number of slits closely placed in a periodic manner, and the diffraction grating gives rise to multiple beam interference, and so we will have very bright spots at a particular frequency, which of course depends on the size of the slit and the spacing between two slits. And this is how the science of spectroscopy developed. And what the Braggs and von Laue, what they figured out is, in a crystal we will have planes of atoms with spacing of angstroms. So, these crystals can act as the slits of a diffraction grating. So, they developed this technique of X-ray diffraction, and in fact the Braggs derived a formula called the Bragg law, which is given by that formula d sin theta is equal to n lambda, where d is the spacing between two planes and sin theta is the angle of the incident X-ray and the refracted X-ray which was forming the bright spot. And so that bright spot is formed only when the X-ray reflected from the top layer and the next layer, they interfere constructively, and that is how we get that n lambda. And so this gave a powerful technique to study properties of materials, because as I mentioned, by the design of the X-ray apparatus, you know the energy of the X-rays, from which I can calculate the lambda of the X-rays, and by looking for the bright spots in X-ray diffraction and fitting it to this formula, theta is measured in the experiment and I deduce the distance between two planes in which the atoms are set in a crystal. So, when de-Broglie proposed that electrons should have wave-like properties, then the obvious thing to do is to see if electrons show this diffraction. So, two sets of people did experiments regarding electron diffraction, one group in the US and one group in England. And what they did is the following: they took a piece of nickel and did X-ray diffraction, and they found and determined the spacing between the two planes in this nickel crystal, and they also calculated the wavelength of the corresponding X-ray, and from that wavelength they also calculated the momentum of that X-ray, and they asked, okay, what should be the speed of an electron so that it will have the same momentum. If the momentum of the X-ray and momentum of electron are the same, then wavelength of the X-ray and de Broglie wavelength of the electron will be the same. And of course, if the X-rays undergo diffraction and give you a bright spot, then electrons, if they undergo diffraction, they should also give you a bright spot. That is the argument. And these groups, they figured that an electron with about 50 to 60 electron volts of kinetic energy will have the same momentum as the corresponding X-ray, and hence the de Broglie wavelength of the electron should be about 1.5 angstroms, and they performed the electron diffraction experiment and found that yes, indeed peaks were observed in the electron intensity as predicted by the Bragg diffraction formula. So, this was a great triumph that de Broglie made this prediction that just like photons have both wave and particle properties, electrons also should have particle and wave properties. And how do we know something has a wave property? We determine it by seeing if it shows a diffraction pattern, and the diffraction pattern using electrons was observed when they shot a beam of electrons with kinetic energy of about 50 electron volts or so on a crystal of nickel, and which verified de Broglie hypothesis. So, both de Broglie as well as the people who did the experiment, they were honored with Nobel Prize soon after. As I said, there are two important properties a wave should satisfy. One of course is diffraction, the other is interference. Now, do electrons show interference also? This turned out to be a much more difficult experiment. I believe the electron diffraction was observed within a few years of de Broglie hypothesis. I don't know, maybe 5 or 6 years, but the electron interference experiment, it took almost 60 years to demonstrate. The reason is, in order to demonstrate the interference, we need to have a object whose size is similar to the de Broglie wavelength, and we find that in order to get an electron beam of We can have in the electron interference experiment, they used a filament. The idea is you have a filament which is about 1 micron thick and you shoot an electron beam, and the two sides of the filament act as two slits. That was the rough idea, and the size of the filament is almost 1 micron. So, we need momentum of the electron such that its de Broglie wavelength is 1 micron. Now, I mentioned a little before, in the case of diffraction, when the kinetic energy of electron is tens of electron volts, the corresponding de Broglie wavelength was about an angstrom. But now I want a de Broglie wavelength of 1 micron, which is 10 power 4 times larger. So, we need to have a momentum which is 10 power 4 times smaller, and we are talking about kinetic energy which is p square by 2m. So, energy should be even smaller, almost 100 million times smaller than that hundreds of eV that we talked about, tens of eV that we talked about. So, which means that you need electrons with very, very low kinetic energy in order to do this experiment. And it took a long time to develop such techniques so that this experiment could be done. That is point number 1. Point number 2. What do we mean by interference? Now, if you look at the derivation of interference formula in any textbook, you say that there is a source, it emits a wave, the wave passes simultaneously through the left slit and the right slit, and then the wave passing through the left slit and the wave passing through the right slit, you add at the screen and then you take mod square to get the intensity, and the mod square shows the effect of interference. So, a crucial aspect to get interference is the wave should pass through both the slits at the same time. But now consider this electron that I talked about. Electron, I have the filament here, electron is coming. Naively we say electron should go either to the left of the filament or to the right of the filament. It can't go both to the left and the right. But if I want interference, I will get it only when somehow the electron splits itself into two and goes part of it to the left and part of it to the right. Only then I will get interference. It sounds absolutely crazy. How can an electron, which we imagine to be a point-like particle with definite mass, how can it split itself, go partly to the left and partly to the right? But that is what de Broglie hypothesis is telling us. If we think of electron as a wave, then it is capable of splitting itself, that part of the wave goes through the left, part of the wave goes through the right, and then it will combine at the screen and give me a signal. Sounds absolutely crazy, but that is what the theory is telling us. And the experiment was done, and this is a schematic of the experiment. You see the filament in the middle and you see the source at the top which is shooting out electrons, and as you see, electron is simultaneously going both along the left of the filament as well as to the right of the filament, and this is the result they get. So, for a detector, and let me briefly describe the experiment. So, the source is such that it emits an electron, and the electron takes something like a microsecond to travel from the, not even a microsecond, it will probably take something like tenth of a microsecond to go from the source to the detector. And so, they have designed the experiment in such a way that the source emits something like an electron, let us say every microsecond. So, you have the electron emitted, it travels, hits the detector and produces a bright spot, and then sometime later the second electron is emitted, it travels and it hits the detector at some other spot, and then you let the electrons go every microsecond or so, so that eventually you let a large number of electrons go through. So, if you see the top left figure, this is after about 10 electrons were passed, they are scattered randomly, and the top right figure, which is after about maybe 200 electrons were passed, again you see a random distribution, and you look at the bottom left figure, which is I think after about a few thousand electrons are passed, and it looks quite random, but you vaguely begin to see some kind of pattern. But the bottom right figure, after something like a million electrons were passed, you clearly see bright fringes and dark fringes. So, which means that yes, electrons, because of their wave properties, they do show interference pattern, and interference means the wave should split itself into two, go through both paths and join together. Only then that is when interference can occur, and that is what is occurring here, which means that the electron is passing both to the left of the filament and right of the filament, rejoining and hitting the detector and forming a pattern. This is completely against how we think of a particle, but perfectly consistent with how we think of a wave. And the first set of experiments in which electron was observed, I mentioned the flow of massive particles from cathode to anode in a vacuum tube, and the E by M experiment of Thomson. So, there one was looking at the particle properties of electron, but the diffraction experiment of electron and the interference of experiment of electron, we are seeing the wave properties of electron. So, just like the photon, electron also has both particle like properties and wave like properties. By the way, the picture I showed, there is a YouTube video, and it is listed at the bottom. So, please watch the video, it is very entertaining and also I must say mind boggling. So, finally, this is the problem. What is happening at microscopic level? Particle or wave, classically speaking, particles form one class of things, wave is a different class of things, and there is no overlap between the two. We have one set of rules by which we describe how particles behave, how they move from one place to another, and a different set of rules as to how waves behave and how they move, how they interact, etc. But in the microscopic domain, it looks as if everything, both radiation in the form of photons and matter in the form of electrons and other microscopic objects, both of them seem to have both particle and wave properties. So, until end of 19th century, as I said, particles and waves were thought of separately. Therefore, one mathematical description was developed to deal with particles and a different mathematical description was developed to deal with waves. But given the experiments which showed in the early part of 20th century, which showed that both photons and electrons have both particle and wave properties, we are obliged to develop a description which can describe both particle and wave properties. It sounds very complicated, but actually it is not that difficult. In fact, a mathematical description already existed. It took some time for people to realize what is the correct mathematics to apply to this situation, and the mathematical description we use is called wave packets, and in the next lecture I will describe how we first define wave packets and how we use them. We first start with some classical examples and we see how wave packets are thought of in classical physics, and then we will develop the rest of the formalism. Thank you.